Common 6 markers. Atomic structure. The core concept. Contrasting the ionization power, penetration depth, and compositions of alpha, beta, and gamma radiation. Example question. Compare the properties of alpha particles, beta particles, and gamma rays in terms of their structure, penetrating power, and ionizing power. Student lesson breakdown. Alpha. Structure. Composed of 2 protons and 2 neurons, a helium nucleus. It has a +2 charge. Penetration. Low penetrating power, stopped easily by a single sheet of paper or a few centimeters of air. Ionizing. Strongly ionizing because of its large mass and double positive charge. Beta. Structure. A fast-moving electron emitted from the nucleus when a neutron turns into a proton. It has a -1 charge. Penetration. Moderate penetrating power. Passes through paper but is stopped by a thin sheet of aluminium, approximately 5 millimeters. Ionizing. Moderately ionizing. Gamma. Structure. An electromagnetic wave emitted from the nucleus. It has no mass and no charge. Penetration. Highly penetrating. Passes through air, paper, and aluminium. It requires several centimeters of thick lead or meters of concrete to absorb it. Ionizing. Weakly ionizing. Half-life context and radioactive waste. The core concept. Evaluating the safety risk of radioactive isotopes based on their half-life and type of radiation emission. Example question. A hospital needs to choose a radioactive isotope to use a medical tracer inside a patient's body. Isotope X emits alpha radiation and has a half-life of 6 hours. Isotope Y emits gamma radiation and has a half-life of 6 hours. Evaluate which isotope is safer to use. Student lesson breakdown. Evaluating isotope alpha. Flaw. Highly ionizing, meaning it would cause severe damage to cells and DNA inside the body. Mutation or cancer risk. Flaw. Weakly penetrating, meaning the radiation cannot escape the patient's body to be picked up by an external medical detector. Evaluating isotope Y, gamma. Benefit. Highly penetrating, meaning the gamma rays can easily pass out through the patient's body tissue to be detected by the medical equipment. Benefit. Weakly ionizing, so it causes minimal damage to cells as it passes through. Evaluating the half-life, 6 hours. A half-life of 6 hours is ideal. It is long enough to complete the medical scan, but short enough that the radioactivity levels drop to a safe level very quickly, minimizing long-term exposure. Conclusion. Isotope Y is much safer and more effective.